Can I start? Okay.
Yes, please start.
Okay. Thanks for giving me the chance to talk here. I'd like to talk about the AdS BCFT from Conformal Bootstrap and construction gravity with particle and brane. This is in a collaboration with LG which is published in GitHub. Yeah, let me first give an introduction of my talk here. Now, main interest in talk is two-dimensional boundary conformal field theory, which is just a conformal field theory with a particular boundary condition called the Cardi boundary condition. There is an interesting proposal about the minimal holographic dual of this boundary conformal field theory by Fujita, Takayanagi, and Tony. In that the holographic dual of boundary conformal field theory is given by a gravity with end of the world brane like this figure, like this figure. In that here we have boundary conformal field theory. Here we have boundary conformal field theory, and the holographic dual has the end of the world brane that arises from the boundary of this conformal field theory. And the gravity action, the Euclidean action of this gravity is given by like this form. In that here we have Einstein-Hilbert action, and this is a heavy particle term, and this is given the Hawking term, which describes the end of the world brane. Yeah, and here we impose the Neumann boundary condition on this end of the world brane. So this object is dynamical, and this dynamics is controlled by this equation. So we can think of this guy as the Einstein equation of this low-dimensional gravity. And there are some interesting issues. There are something that that are not so well understood. Yeah, I will give some examples of what is not so understood in the gravity with the brane and heavy particle. The first one is brane self-intersection. Yeah, let's consider the gravity with end of the world brane like this figure. And if we induce a heavy particle in this geometry, then we have a gravitational interaction between the brane and this particle. So as a result, what happens is that this brane is bent by this particle by the gravitational interaction between these two guys. So yeah, there's a possibility that this brane has a self-intersection like this. But this configuration seems to be a little bit strange, so we would like to avoid this configuration in some way. But for now, we don't have the understanding of the mechanism. So yeah, I will explain it later about the more details about the brane self-intersection. Yeah, and also we don't know what happens. We don't know what happens if we consider negative tension brane. The definition of the tension is this guy. In that tension is the Lagrangian term of this, the Lagrangian of this on this end of the world brane. And if we consider the negative tension brane, then what happens is that as we decrease the tension of the brane, then there's a possibility that this brane attaches the world line of this particle. So a natural question is how to understand the world line behind this end of the world brane, that this one. And also, we don't know how to deal with spinning particle in the gravity with brane massive particle. On the CFT side, it's obvious that one-point function on the disk should vanish if we consider non-scalar primary because of the rotational symmetry. Yeah, and on the gravity side, actually, this can be translated into this property in that the spinning particle cannot end on the end of the world brane. But unfortunately, we don't know the mechanism of how to exclude this configuration on the gravity side. A part of the reason is because actually we don't know how to deal with the spinning particle in gravity with end of the world brane. And so here I would like to give the answer I would like to give the mechanism of this problem, of how to resolve these problems, and And in this talk, actually, I would like to address these issues by using the conformal bootstrap equation through the AdS BCFT. And I would like to emphasize that in fact, there are many loopholes in gravity calculation, as you can see in various previous papers. So it is worth checking compared to robust results in the results from the conformal bootstrap equation. Here I will give a quick review of boundary conformal field theory. In a similar way, to conformal field theory, actually we can evaluate any correlation function with the few information, few CFT data in that in CFT, in just a standard CFT without boundaries, any correlation functions can be evaluated only with the information about central charge and spectrum and OPE coefficient. Now something similar happens in boundary conformal field theory. In that any correlation function in boundary conformal field theory can be evaluated with bulk OPE coefficient and bulk boundary OPE coefficient and boundary OPE coefficients. Here I mean bulk by the bulk primary operators that is the same as that appears in CFT without boundary, and I mean boundary by boundary primary. Which is a new object in boundary conformal field theory. In that, this is just the primary operators that lives only in boundary. This is an example in that, for example, if we would like to evaluate a two-point function on a disk. If we would like to evaluate the two-point function on a disk, then what we need to do is to consider a cut along this yellow line. Or here we just consider insertion of complete set, bulk primary complete set, bulk operator complete set. And then as a result, we obtain a product of one-point function on the disk and bulk three-point function. In that, we can express this two-point function on the disk as this form. In that, here we have a bulk boundary OP coefficient and bulk OP coefficient, and this is so-called the Villa-Solo conformal block. And this is something like this is a special function. This is a special function, something like a hypergeometric function. So this does not depend on theory. This is completely fixed by the conformal symmetry. And moreover, actually, this Villa-Solo block is completely the same as the Villa-Solo block for four-point function on the disk with a boundary. This is because by using the mirror method, the word identity for a two-point function on disk is completely the same as the word identity for four-point function on the sphere. That's the reason why here we have just the Villa-Solo block for four-point function on disk. Not a sphere. We have another way of how to count this correlation function, in that we can also consider insertion of boundary primary boundary operator complete set along this line. Or equivalently, here we consider bulk boundary OPE coefficient like this one. And then we obtain a product of bulk boundary OBE coefficients like this, in that we can express this two-point function on disk as this form. And here we have bulk boundary OBE coefficient, and this is the third conformal block. Here we may obtain a little bit trivial equation from the same two-point function on disk. In that, we have two ways of how to cut off this two-point function, and so we have two different expressions from the same two-point function on the disk. Yeah, this seems to be a little bit trivial. But interestingly, actually, this equation gives a non-trivial constraint on the CFT data. This is called the conformal bootstrap equation. And here in this talk, I'd like to use this conformal bootstrap equation to address some issues in gravity with end of the world brane and particle. Okay, let's go back to our interest in that. Let's consider the gravity with end of the world brane. Here, this is the gravity toward boundary conformal field theory. And as I mentioned before, if we put a heavy particle in this geometry, then we may have a self-intersection like this. And actually, we can give an explicit condition to where the self-intersection happens. In that, if we use the relation between the mass of particle and the conformal dimension of the corresponding primary operator, then we can argue that the self-intersection happens if we consider the primary operator with conformal dimension rather than C over 32. Here the relation is given by like this. Here the relation between the mass of a particle and the conformal dimension is given by like this. And this self-intersection problem has been pointed out by various papers. And in particular, the first one proposed that, we would like to exclude this possibility. So this one proposed that primary operators in this with the conformal dimension in this region should be excluded in holographic CFT. Okay, if this is true, then we may be able to find the same constraint by using the conformal bootstrap equation, maybe. So we would like to address this issue on the CFT side. Okay, now let's translate our interest into in the CFT language. Our interest is the adding mass of this geometry, and here I'd like to emphasize that this adding mass is not so trivial in that this adding mass is not given by just the mass of this particle. Here we consider this setup. In that here we have a particle, and here we also have the end of the world brane. And the adding mass of this geometry is not just given by the mass of this particle. This is because here we have non-trivial gravitational interaction between this particle and the end of the world brane. This makes the adding mass a little bit complicated. To solve the bootstrap equation, actually we need a few inputs. And here our assumption is following. We assume that there's no interaction between particle and the end of the world brane, except for gravitational interaction. And actually this assumption is true because there's no matter interaction terms in our Euclidean action. Okay, in the CFT language, this assumption is expressed like this form, in that bulk boundary OPE coefficients with the vacuum boundary should be vanished except for p equals 0. And actually, this is possible at least in the case P not equal P. Yeah, with this assumption, let's solve the bootstrap equation. Yeah, this is now bootstrap equation, and now interest is the added mass of this that geometry, and this if we use the relation between the added mass and the conformal dimension, then yeah, actually the added mass corresponds to the conformal dimension of the intermediate state. The conformal dimension of the speed. In particular, the added mass is just given by the lowest conformal dimension that appears in the sum. And to evaluate this guy, then actually it's very useful to consider the dual channel expansion like this. This is because here we have CP0. This is completely the same as this one. So we can use this assumption to evaluate this one. Actually, this is much simplified, and this is just given by just the vacuum block with that assumption. And we know, we know the dual channel expansion of this Vila cell block because, as I mentioned before, this is just a special function. This does not depend on theory. Yeah, this one is called the fusion transformation, and here I use the Liouville notation for simplicity, but this Liouville momentum is directly related to the conformal dimension by this equation. Yeah, anyway, this is kinematic object. So this fusion kernel, the kernel of this integral transformation is also completely fixed by the conformal symmetry. In that we know the closed form of this guy. Now these two ones expanded in the same basis. So we can identify the mass spectrum by just comparing these two guys. In that this coefficient is the same as this one. In particular, we obtain this relation. The added mass is just given by the Liouville momentum of this. The added mass is just given by the twice of Liouville momentum of this external primary operator. So over equivalently, we can say that here we obtain the relation between the added mass and the mass of a particle. In that the added mass is just given by something like this, and this can be expressed by using the mass of a particle. By using this relation, actually we can argue that if the mass of a particle has the conformal dimension rather than C over 32, then the added mass it becomes rather than C over 24. This implies that actually, if we consider this heavy particle, if we consider some heavy particle in this geometry, then the black hole forms in this geometry. And actually, this bound completely matches. This bound completely matches completely matches the self-intersection bound. So we can finally conclude that the self-intersection can be avoided by the black hole formation like this. Yeah, we can learn more from the same conformal bootstrap equation that we can give the relation between the added mass and the mass of a spinning particle like this one. And also we can find that the relation between added mass and the particle mass does not depend on the tension of the brane. In that our relation between added mass and the particle mass is true, even if we consider the negative tension brane. This seems to be a little bit interesting because, in some paper it has been proposed that if we consider negative tension chaos, then actually, something, on the gravity side, there seems to be a transition in that there seems to be a drastic change. If we decrease the tension in that the brane can attach the word line of the particle if we decrease the tension. So this one has proposal that the boundary primary spectrum should be drastically changed if we consider the negative tension brane. And so this transition might be able to detect it by using the conformal bootstrap equation. But actually we know the answer. We know the answer in that the bootstrap equation answers the no transition. This is the result from the conformal bootstrap equation. Let me give the explanation of this result, this CFT result from the gravity side. And to do this, actually, we need to construct a gravity solution. And in standard case, actually, we don't need to explicitly solve the Einstein equation because what we need is only the in standard case, actually, we can use the Fifferman-Graham expansion. So we don't need the explicit form of the solution to the Einstein equation. But in this case, actually, we need the information about the configuration of brane. So we need the information deep into the bulk. So in general, we need to solve the Einstein equation explicitly if we would like to understand the brane configuration, or if we would like to discuss some problems in AdS BCFT. But fortunately, in this case, actually, we can construct the solution in a simple way called the cut-paste procedure. Actually, I don't have enough time, so I don't give the detailed explanation of how to construct it. So here I will give a quick review of how to construct it. For example, let's first consider the simplest case in that if we would like to construct a conical defect geometry, then what we need to do is just to consider a cut. Here we consider time slice of global coordinate, and here we consider cut of this geometry. And the angle is related to the mass that appears in this Euclidean action. And if we paste, if we identify these two lines, then we obtain a conical defect geometry. And actually we can show that the eddy mass matches that we expected. And actually, we can construct the conical defect geometry with the end of the word brane in a similar way. In that, let's first consider the gravity with the end of the word brane. And if we would like to induce a conical defect, then what we need to do is just to cut this geometry. But the circumference of the asymptotic boundary becomes a little bit complicated compared to this standard case. So as a result, actually the eddy mass of this geometry becomes a little bit complicated, unlike this one. But actually, this eddy mass, as you can see here, actually the this eddy mass is just expressed like this form in the CFT in the Liouville notation, and this completely matches that we obtained from the conformal bootstrap equation. So this construction is consistent with the conformal bootstrap equation. Actually, we can also construct a spinning defect geometry in a similar way. What we need to do is consider the twisted identification. In that, we consider the twisted. We consider the identification with around different time slices among different time slices like this. And yeah, actually we can reproduce. And actually by using this construction, we can show that the self-intersection bound in the self-spinning particle geometry is given by like this form. And the point is that this bound completely matches that we obtained from the conformal bootstrap equation. So this construction is also consistent with the conformal bootstrap equation. And also, yeah, we can answer this question by using the same construction. In that, yeah, our construction by using the two-state identification leads to a mismatch of brane. Yeah, such a singular configuration cannot be a solution to the Einstein equation. So yeah, this mismatch here explains why one-point function on the disk should be vanished if we consider non-scalar, if we consider spinning particle. Finally, let me give an explanation of the negative tension, let me give an explanation of how to deal with the negative tension brane. Yeah, we found that actually the conformal bootstrap, that the answer from the conformal bootstrap is opposite to that we expected in, for example, in this paper. Yeah, that is proposed in is opposite to some proposals in previous papers. And now question is how to understand this result from the gravity side. And actually, we can also construct the conical defect geometry with the negative tension brane in a similar way. And let's first consider the gravity with negative tension brane like this. And let's consider a cut of this geometry. Actually, in this case, something strange happens in that here we have some corner singularity on the end of the world brane. Yeah, how to deal with this geometry is yeah, we can deal with this geometry by just adding the generalized Hayward term like this one. And here we have additional parameter TC. This is the tension of this defect, and yeah, we have additional parameter TC, but this is not free parameter because for the action to have the solution to the Einstein equation, then this TC is dynamically determined by this mass and tension. So this is not free parameter. And also by using these properties, actually we can identify the adding mass of this geometry with negative tension brane and heavy particle, and actually we can show that the adding mass is just given by this comparator matches that we obtained from the CFT side by using the Conformal Bootstrap equation. So yeah, we can conclude that the adding mass is non-sensitive to whether the tension is positive or negative. So yeah, this is what happens for negative tension brane, in that the singularity behind the end of the world brane appears as corner defect on the end of the world brane like this one. And yeah, the point is that this construction is completely consistent with the conformal bootstrap equation. So we are sure that yeah, this construction is definite. Let me finally give the discussion. Yeah, future direction of this result. Yeah, in this talk, actually, we only consider one bootstrap equation. One bootstrap equation is the bootstrap equation for a two-point functional disk. But we know, yeah, actually, there are 6 fundamental bootstrap equations in BCFT. So we may be able to give more consistency conditions on branes from other 5 fundamental bootstrap equations in boundary conformal theory. And the second one is, yeah, here we present the way to induce spinning defects on gravity with branes. Yeah, this construction can be applied to study more various setups, including spinning defects. there are some yeah, the interesting issues. Yeah. Anyway, yeah, that's all. Yeah, thank you very much.
Thank you, Yuya.
Yep.
Sorry,
Yep.
time is over. So if anyone has questions, please contact directly with Yuya. All email address of participants are available in the